Hi, and welcome to QCon. Those of you who are joining online, today I want to talk about real-time ML pipelines and how to build projects that involves machine learning and real-time data. We're gonna talk about the landscape in streaming, all different architecture decisions you can do, and advantages and disadvantages of each solution. I'm Thomas Neubauer. I'm CTO and co-founder at Quix. And before I worked in McLaren, where I was leading a team that was connecting F1 cars to the factory, to the cloud. So people in a factory can build real-time decision insight on top of telemetry from F1 cars without traveling every second weekend to the track around the world. Now, this was quite challenging use case because the amount of data coming from sensors were enormous. There were roughly 30 million numerical values per minute per car, and some of the sensors were particularly high resolution, more than 1 kilohertz. That means more than 1,000 numbers per second from only one sensor. And we quickly realized that database solution and database-centric architecture will not work because we couldn't simply find a database that will be able to persist and query this amount of data at this scale. So we were kind of forced to look around, and we adapted streaming. We adapted Kafka as a broker, and we successfully connect sensors from a track to the cloud, and people in the factory could use it. But the problem was that our team was truly cross-functional. So we had chassis engineers, mechanical engineers, simulation engineers, data scientists, ML engineers, and none of them really liked how Kafka worked, and they couldn't really leverage the power of this technology because they mostly use Python, and every tool for Kafka was in Java, and that was really we're not really using the potential fully. And this is where really I first thought about, well, there's a gap in toolset around Kafka start to grow. So today I want to build with you this simple demo. We're gonna have a application running on the phone here, and it's a fitness app that's sending GPS location, speed, altitude, heart rate, G-force data from all dimensions. And we're going to detect cyclists crashing with this fitness app on a bike. And we're going to display all of that in a simple front-end application. Now the question is, how are we going to build this? What's going to be the architecture? Well, there's a couple of options we can do. So first, we need to choose between streaming or batch. So if we go for batch, it's probably going to look like this. So this is AWS example. So imagine you have multiple phones sending data. You deploy API gateway to the edge, and you send data through it into something like a Kinesis, which will funnel data to S3 buckets. And that data you can then load into your SageMaker and analyze it, and later use it to label the data and train the model. At the end of that training, you will end up with a pickle file that you will then deploy to Spark into a step function where you're gonna, in batches, load the data from S3 bucket and analyze it if there's any crash in it. And later, you will output the result to another S3 bucket where you use AWS Lambda to push it to front-end application, again through API gateway. Now, as you can see here, it's database centric. We have S3 buckets everywhere. So another problem is that you can imagine that there will be delay between the phone and actual information displaying in a front end because we have pooling involved in this pipeline. We have problem of vendor specific technology. So if you want to migrate this to different cloud or possibly on premise, we're gonna have a lot of work migrating Kinesis to Azure or Google technology, etc. And lastly, databases are not really great for scale. If you really need to get to high traffic, database is going to be the bottleneck of your architecture. So if we go for streaming, the architecture is going to look a bit differently. Well, at the beginning, it is the same. We're going to use WebSocket Gateway because that's the right thing to do. But then we will send this data to a topic in a broker, in a Kafka broker, where we're going to first sync it to database. So we can load it to Google Colab or SageMaker and use it for analysis and model training, which at the end we produce again a pickle file which you can use in our service. Now if I go to such a Jupyter Notebook, here you can see that my colleague loaded the data from the database, and here we have GeForce data for all dimensions, and we label them if it's shaking or not shaking. Then we plotting them to see what's going on, some analysis of all sensors there. We add some features to the data. We use TensorFlow then to train the model. Then we backtest unseen data to see a possible bias. And at the end, we will package this in pickle file and publish to model registry, in our case, a blob store. So going back, this is basically where we get the pickle file, and then we can deploy it in the service. They're going to real-time process data coming from the phone data topic and output the results to alerts topic. So this is basically where we are using the model. And then the rest is same. We send it to WebSocket Gateway, and then we send it to frontend. Now you see, the difference here is we don't need a database to actually detect crashes. The moment we train the model, we can even disable the persistence and completely forget the database, it's gonna work. So now instead of database, the center of our architecture is broker. Apache Kafka, for example, which is highly scalable and resilient technology. So when you're deciding between batch and streaming, you might be thinking it's just about different technologies in your architecture, but actually it's more than that. It's about the approach to solving common problems. It is about the mindset when you're building your pipeline. So imagine a very simple operation where we want to calculate a delta between forces applied to the phone between all data points. So as a byte going around, it's sending data points, and they are being collected in database, and in a batch would look like something like this: a table with rows where each row has a timestamp and values in the columns. Now we can quickly add a new column that would be a new feature calculating a total force applied to the device, and that's easy. And then we can do a delta on that column, and here you see we just get the previous row value and subtract it. In streaming though, we don't have a table. As data being collected, they just go straight to the pipeline piece by piece. And that means that we can calculate a feature, that's easy, that's a stateless operation. But then for a delta, we're gonna need to process state, because the next time we're not gonna have this row of data available. So obviously for the first row, we can't calculate the delta. That's the same with the batch. But with the second data point, we lost the previous values, but we have a state. And so now we can calculate the delta with the previous value. And then we update the state and we continue in the same fashion. Now, what is here, the complicated thing, is to make the state persistent in case of restart. And that's actually not a trivial thing to solve. And we're going to talk about that a bit later. So this is obviously a machine learning use case. And when you're building ML-powered architectures, you have two major options to deploy your model. API, web API services, and streaming. If we zoom in into the model, it looks like this. You have inputs with the feature, you're calling the API, and the response is if it's crash or not. Now, what are the issues with such an architecture? Well, first of all, let me just move my... first of all, CPU overhead on every call. So this phone that I'm gonna use today for the demo is gonna send 4 Hz sense data, which means that 4 times per second there will be a message. Now, if that's 100 phones or 1,000 phones running at the same time, you see there's a lots of requests, and that will cause unnecessary CPU on orchestration of those requests. It's also introducing delay because each HTTP request will take time to be processed by the middleware. But the biggest problem is really what's going to happen if your service can't handle the traffic. Well, first of all, it's going to slowly get slower and slower to respond to the request, and until it's reached the point when that is longer than the timeout on the client, and you're gonna start losing the request, and basically that's a disruption in service, and you're losing your data. You can obviously scale your API services, but you never can predict what traffic you will get. With streaming, this is no longer a problem because service is running straight on top of Kafka, and therefore we can leverage Kafka temporary persistence and checkpointing system to make sure we're not going to lose any message. If the service will get overwhelmed with the traffic, in the worst case, we will get the answer a bit later, but we will never miss a single message. So here we're directly embedding the model into a streaming service, and that is more resilient and more scalable solution. So if we're gonna do that, we're gonna build a stream processing application. Now that means we have to choose one of the architecture design for such a project. The first is using Kafka client libraries that using Kafka producer and consume API directly. That's a lightweight, elegant solution, but has its downsides. The second option is to adopt full-fledged stream processing framework like Apache Flink, but that's also not a silver bullet. So with the Kafka producer and consume API, it works very well with a simple processing when you process message by message without any context. You can use it in any language and you don't drag any dependency to your architecture. The problem is when you start using stateful processing, when you need to get a state and context and getting the data from multiple messages. That is super complicated and is a proper software engineering. And this is the moment when you might be tempted to use something like Flink. So with these full-fledged stream processing frameworks like Flink or Spark, you basically running your processing in a separate cluster, in server-side cluster where data and codes get redistributed by the engine and executed in a scalable and stateful and resilient manner. The problem is that you bringing a Java dependency, and the whole ecosystem is really JVM. So that means it's quite difficult to use from Python. And also debugging is quite difficult because the code is not running in your IDE. The code is running in a server. Then it gets really complicated when you try to combine the classical world, for example, Kubernetes deployments, and your Flink jobs. You just can't slap the Flink code to your existing microservice because it's not running in that Docker container together with your Node.js, Java, C# microservice. It's running in Flink. So when you use these frameworks from Python, you will get common problems like, for example, handling jar files. And even though you have a way of connecting, for example, Flink to Kafka, you need to use Flink connector. And therefore, if your Kafka is configured with some more advanced settings like Kerberos or certificates, SSL, then it gets really difficult to use. And then if you get over that, you might be thinking, this is pretty cool. I can do SQL and that's powerful. But until the moment, you need to do something real, because then you have to build custom functions, user-defined functions. And if you build them in Python, the problem is that because it's a JVM engine, they have to run Python environment on the side and connect it to some socket connection, as you can see here on the official documentation from Flink. And that's obviously not ideal. And if you have any problem, trying to understand the errors is super difficult. And what we really need and want, I think, is debugging, going line by line and see what is going on, why my code is not working. So question is there a third way? Well, we believe that there is, and that's why we built and created a new library called Quix, which is basically something between the lightweight libraries and full-fledged stream processing frameworks. So it's still light, it's still just a library, but it starts trying to solve the more advanced difficult problems by leveraging Kafka and its features. So what is our approach then? How am I going to build this demo today? Well, I'm going to leverage Kafka, Python, and containers in Kubernetes to build resilient, scalable solution. And the most important concept to grasp to understand the demo today is what sometimes is called pub and sub service. It's basically when we subscribe to topic, we load the messages, process them, and we publish the output of that processing into another topic. Why this is a good idea? Well, first of all, it's a very scalable solution. Those partitions are redistributed in a cluster, and each topic consists of numerous partitions, and data gets redistributed in those partitions. And then they are assigned to multiple instances of processing code running in the containers in a deployment in a Kubernetes. So here we get each instance getting third of the traffic, and you can add more and more to horizontally scale this processing. And it's fault tolerant. First of all, those partitions get replicated twice, 3 times based on your configuration. So if one of the nodes in a Kafka broker fails, streaming is ensured, but also your compute deployment get replicated, and when you have a restart, others will take the traffic and the failed container will get scheduled again. So it's resilient and scalable solution on a data delivery and compute side as well. Cool. So with that done, let's switch to the demo and let's try to build real-time application powered by machine learning. Cool, so now we are in my PyCharm, and here we have a starting template for Quix streams library for processing code. The Quix streams library is the third way, and here I'm just going to run the code and see if we getting data. So I'm here running my companion app, which is sending telemetry data, and if I just move this to the right, there we are. We can see we have a stream coming from Thomas' phone. So that's good. So if I stop the code, and here I can start building my service. So first of all, I'm gonna get a data frame. It's not real Panda data frame, it's a streaming data frame, but it has the same interface. So we can use the knowledge we have from batch in streaming. So here I'm gonna get GeForce X, GeForce Epsilon, and GeForce Z. Cool. So then I will print the header, and then I'm going to iterate rows as they being streamed to the pipeline. Cool. There we are. So if we go to the top, we see here 4 columns, and now the data being streamed. And if I take the phone, you can see that immediately changing based on me moving with the phone. So we have data connected to my code. So first, you see that sometimes we have gaps. That's because not every row contains these 3 columns. So I'm gonna do a filtering here, and I'm gonna say when it's not none. And then we're gonna need to create a new column. The column is called GeForce Total, and we saw that in Jupyter Notebook, and that's basically a total amount of forces applied to the phone from all dimensions. So So here we're gonna just do an absolute value of there we are. Cool. And last, to get something meaningful information from this column, we're gonna calculate a 10-second rolling window to see if there are substantially more force applied for some longer period. So let's call this column GeForce Total 10 seconds. And that's gonna be, again, classical pandas. And because we have already quite a lot of data, I will just adjust the print width to 15, and let's start it. There we are. So if we go to the top, we see we have now these columns. And if I go to the bottom, you see the rolling average is 9.9 G's. That's because we are on planet Earth and we have gravitation forces. But if I start shaking with my phone, you see it's going up. And if I put it back to the table, it's going down again. Now, what if I now stop the service and restart it? Well, we definitely don't want to start from 0 because we would lose some data. Luckily, the library would take care of the state and use the Kafka checkpointing to make sure that we will recover from the same state. So I'm going to start checking to get some numbers. There we are on number 16. And now I'm going to stop the processing and I'm going to start it again. And you see that we were on the 10 and now it's going back to 9. So if I go back to the top, we were starting on 17, 16, 14, 12, 10, and 9. So the first row is recovering the state of the previous run. This is what we want. Cool. So now it's time to use machine learning model. So I'm gonna just borrow a code here from my notes to get the model. And here on the top, and then I have here how to call it, so I have to do it here. Cool. All right, so now I'm just gonna create another column called shaking. So obviously we are not crashing here a bike in my office, so that's why we detecting shaking and not crashing. Maybe I haven't mentioned that in Jupyter Notebook explanation. So here, there we are. Cool, so the number 0 tells us that there's no shaking. And if I shake now, you see there's ones, which means it's successfully detecting my shaking. So that's working. If I can try it again, amazing. Now, the last bit we want to do here is get this information to our product. In our case, in this demo, a simple front-end application. So here, I have a front end, and if I refresh it to see just current session, there we are. You see I'm in Prague, and you also see the GeForce informations here coming from the phone. Now, if I shake, there will be nothing because we haven't write the result to the output topic yet. And to do that, well, that's just one line of code. So here, I will get the output topic, so the output stream, right row. And because it's an asynchronous operation, I will do that. And then cool. So now if I shake, there we are. We have crash detected in our front end. So the mission is completed. Amazing. So I hope you enjoy it. And obviously, if you want to try it at home, all of this is open source code. It's in our library. And also here, I have a QR code. If you want, you can scan it and clone the library and just try it and give it a try IDE. Thank you very much for listening and watching my presentation, and bye bye.